So for everyone who isn't familiar, Felipe is our CTO and kind of the original architect of BlazingSQL and everything that we started doing about, I want to say like 6 years ago when we started playing with GPUs for the first time. What he's going to talk about today is a little bit around our out-of-core technology, which basically enables us to scale up query execution beyond what's available in GPU memory. That's basically it. So Felipe, you can take it away. And yes, real fast for any of the questions, you can ask questions here in the chat. There's actually a Q&A feature inside the Zoom webinar. So if you are inside Zoom, the best thing for you to do is to submit a question to the Q&A platform. You can see it at the bottom of your webinar feed. And that way we can manage the questions and answer them. But if you can't find that, the chat also works, but the other is definitely better. All right, Felipe, with that, it's your session, mate.
All right. Hi, I'm Felipe Aramburu. As Rodrigo said, I'm the CTO at Blazing. And what I want to do with everyone today is run a couple of simple queries, look at their execution plans in Blazing, see what that graph looks like, and get an idea of how Blazing handles out of core, basically what it is that Blazing does when we start having memory pressure, right? When we start running low on resources. That's really going to be like the majority of my talk. Is I'd like to explain to all of you how we handle this and why we've made some of the decisions that we've made, and of course to answer questions that you all might have about that. So quick introduction that we always like to give people about RAPIDS is RAPIDS is a Python ecosystem that helps accelerate data science, ETL workloads with GPU accelerated libraries. BlazingSQL is a SQL component of that, but there are many other components. Many of them are open source. And right here, we can kind of see like some examples of what those packages are. For those of you who don't know, we all work off of the same in-memory GPU representation of data, which is based on Apache Arrow. And so all of the libraries here and many others, including Graphistry, for example, can interact with that GPU representation natively and don't have to do any serialization or deserialization to move information between BlazingSQL and a QDF function or a QML training session that you might want to have. Yeah, so that's kind of like a real rapid introduction. BlazingSQL is the SQL engine in this ecosystem. We are the way that you can interact with these data frames on SQL. And this is kind of what, not kind of, this is exactly what it looks like to run BlazingSQL queries. You make a data frame. You don't have to only make a data frame. You can also just pass the files directly to the create table statement or pass it a list of directories or use wildcards and what have you. But the idea is that you create a table based on files, right? Files that exist that you have somewhere, and then you can run queries against them. And the result of this query is a QDF. It's just like, you know, pandas, like when you run this query, the output that you get is a data frame in QDF that has, you know, it's just a normal QDF. The output of this is the same type as the type DF up here, right? The output of bc.sql is the same as the output of data frame. We like SQL for this kind of data manipulation because of many different reasons, right? It's accessible, concise, it's powerful, it's optimizable, it's much easier to optimize than for example, just straight up Python code. And we did a few things that are gonna kind of help make this scale a little bit better, and that will necessitate the need to be able to do out of core processing. And that's that we access that data where it lies, right? So S3, HDFS, we go after your information where it's lying. So it can actually scale to very large storage systems. We look at it how you store it, right? If it's an ORC or Parquet, CSV, we don't care. We're reading the information in the format that you picked, and we're trying to help you guys be as big as is needed. So the way that Blazing works is that when you start out with something that's like a query, which gets converted via Apache Calcite into a relational algebra plan. That relational algebra plan gets converted in Blazing into a physical plan, and that physical plan generates a graph that looks something like this, right? So we'll have a scan. Here is a table scan. And in between the project that's about to come after it, which does something like row-wise operations, like let's say I'm going to scan table A and then I'm going to sum the first and the second columns, right? The project would have the operation that does the summing of those columns, and the scan is what actually reads the files from, disk or from HDFS, or which brings in a QDF data frame from another process. And in between the scan and this project is a cache node. This cache node basically provides the following functionality. When scan generates a data frame that needs to go into the next kernel, into the next project, we don't always know how much space we're going to have, how much space we're going to need, how much that project might explode. So we need to be able to kind of monitor our resource consumption. And when things are pushed into these caches, these green boxes, we want to be able to decide where they're going to go for temporary storage, right? So the project might not need it right away, right? It might be busy processing some other chunks. So something that can happen in Blazing is that in these green squares, when a data frame comes in, it can get moved either to the CPU or the disk. It can also stay in GPU, but it can basically get moved into any one of these three layers in order to be able to have access to more resources. So that we don't have to rely just on GPU memory for all of our interim materializations, for the inputs and the outputs. We can actually run this analysis we can divide up these really large data frames into smaller pieces so that we can make sure that everything fits in memory, so that we're able to solve bigger and bigger problems. I'm trying to see if I have any other points here. Nope, that's it. So I think after this, what I'd like to do is show you guys what this kind of plan looks like in Blazing by going into app.blazingsql.com. And this is the point where you guys can open up the notebook that has been shared with you. So if you've cloned that notebook, I'm going to give everyone just a minute or two to get this open, and then we can get started running these queries and seeing what the relational algebra looks like and whatnot. Rod, that's a good idea, right? We should wait a second here.
Yeah, I was trying to get myself off mute. So if you haven't already, you can clone the notebook via that command that I put both in the Zoom chat. I'm going to put it one more time. I don't know if people that just joined can see the history of the chat. So I'm going to put it one more time in here. It's also in the RAPIDS Go AI. You can execute that from a notebook cell. If you take out the exclamation mark, you can just open up a terminal window in app.blazingsql.com and run that in the terminal. Real fast, also just to let people know where that notebook is, because that notebook is a couple of directories in. You should see that there's a tutorials And then in tutorials, there's multi-GPU, and there you should be able to find this notebook, which will be called a little bit different than what Felipe's is called. It's called BSQL_RA for Rapids Academy _TPCH SF100. So if you can't find that right now, please either raise your hand or chat us directly inside Slack or here so that we can support you. And Felipe, you don't worry about that. Leo and I'm monitoring that Slack.
I was about to go check and I was like, no, I'm not supposed to do that right now.
Yeah, don't worry about it. So let's give people just one more minute real fast, and then we can go over it. You know what? While we're waiting, this is a perfect time for a question that came in. So one of the first questions is, why would I use BlazingSQL if I can do things I want in Pandas or cuDF?
Sure. So there's a couple of answers to that question. One, it's a lot easier for us to optimize SQL and to avoid many interim materializations, many places where if you use cuDF, you're going to be going to global memory, where we can basically fuse those operations together. The other point is that we handle out of core a much more, I would say, with a bit more robustness than happens with just cuDF. For example, when you're making cuDF, when you're trying to do DAS cuDF stuff that's out of core, it works perfectly fine if it can kind of divide up that problem beforehand and divide up the outputs. But your interim steps need to fit in GPU memory, or it will go and give you a big complaint. We don't have that issue. The other thing is that for me, I can express more data manipulation in fewer lines of code in SQL than I can in what do you call it, in Pandas most of the time. That might not be true for another person. You might be some Pandas guru. That's not me.
Mm-hmm. Yeah. So just to add to that, it's kind of a pick your poison. That's what's so great about the data frame. You can either go Pandas like API, or you can go SQL. I think that's enough time to give people, Felipe. So why don't you jump in and I'll try to triage anyone who's having issues.
Sure.
Oh, and tell everyone how you opened up that GPU resources thing, because someone literally just asked about it.
So it's right here. You click on the system dashboards on the left. It's the little thing that looks like, I don't know what that icon
looks like a GPU. It looks like a GPU.
I could be.
Yeah,
sure.
That's what it's supposed to be.
Ah, nice. And then you click on GPU resources and that'll open that up. Great. So, I mean, first thing we do usually is kind of see, hey, here we go. We've got a T4 running. That's the GPU that we're going to be running this on. And then the next step is that we're creating our context. Here, we're basically limiting the amount of memory that we're going to allow the context to use. We're going to allow Blazing to use. And this is going to force it to start using the cache earlier than it normally would, just so that we can make sure when we look at the logs that we are definitely going into the CPU. When you create here, I'm setting pool equal to true. I'm going to just, it doesn't matter. I think that you all have that. It's not going to be very important for this demo here. But we'll go ahead and initialize that. And once we do that, our context is ready, right? So that means that Blazing is now initialized. You can do things like create table, register file systems, and run queries. The first step after we create our context is to register the S3 bucket that is going to have the data that we're going to be referencing. So we'll go ahead and do that. And it kind of basically just let us know that it was able to register that bucket successfully. And then here we're going to create tables based on all of this, on all of the data that we have in S3. I never explained what kind of notebook we're looking at. So let me back up 1 second. This is a TPCH demo. So TPCH, for anyone who doesn't know, is an industry standard benchmark for databases. It's used to kind of see how databases perform in a wide variety of situations. And here we're looking at a TPCH benchmark, which is based on a 100 gigabyte data set. So we're using about 1.6 gigabytes of memory of this GPU, or 1.5. So it's using 10% of whatever the total memory here is. And we're using that to query a 100 gigabyte data set. So first thing I'm going to do here is, now that we've registered the S3 bucket, we're going to go ahead and create tables. This kind of data is kind of like retail-ish data, right? It's like, oh, I have a bunch of orders and each order has line items on it. I've got customers, parts, and things like that, geographic information. This takes a little bit of time. We're working on optimizing this by being able to leverage the underscore metadata directories that Parquet sometimes offers, but for now it's going to take a little bit of time. But after 23 seconds, it's gone through and read all the metadata on those tables. It knows where all the row groups are. These are Parquet files, if I'm not mistaken. And now that we've done that, we're going to want to run our query. So this is what a Blazing query, looks like. It's just SQL, the kind of SQL that you're used to. You'll notice that I'm printing out the explain of this query. So we want to look at the relational algebra to get kind of an idea of like what it is that is happening in the graph and what that's going to look like compared to some visualizations we're about to see. So we're going to go ahead and run this. I probably should have started this before I explained all that, because this one takes a little bit of time, but you should start seeing both the algebra and a result for this query after about 30 or 35 seconds. So what Blazing is doing here is it's taking all these files, right? We see that there's these three tables: customers, orders, and oh, I think we might have run out of memory because there's a bunch of people hitting the machine I'm on. I'm just gonna refresh here. See if it puts me on a machine that's not quite as in use. Go ahead and recreate these tables and run this query again. app.blazingSQL.com is something, it's not new, but it's definitely something that we've been working on a lot recently. So we're definitely expecting to see a lot of improvements and better scalability as more and more people get logged on to these to this shared resource. I'm just going ahead and recreating these tables and running this query again. I'm hoping that we don't run out of memory or something. Yeah, are there any, Rod, you can tell if there are questions, right? So if there are any questions that you want to throw in while we're waiting for results, that's always helpful.
Sorry, I disconnected for a second. What was that? What did you ask? If there are any questions?
Yeah, if there are any questions,
I've got more questions. Yeah. So how does BlazingSQL fit my use case with all data being stored in a Postgres database?
It doesn't fit your particular use case at this time. You would want to export it, but Rodrigo is going to say something better, I think. So go ahead.
Yeah. So real fast. Like Felipe says, yeah, you'll want to output that to QDF or Pandas, ideally, or even Arrow, to then be able to run BlazingSQL queries off of it. our long-term vision is to be able to create tables off of databases. One of the first examples of that is with Hive, which we built out for a customer. So for example, you can create tables off of Hive cursors so that you can query directly on databases, but we don't have anything like that for Postgres. Felipe, your query just ran though, so you might want to talk about it.
Yeah, so here we have two outputs here. This is the relational algebra that we got from Calcite that we actually used to generate the graph and execute the query. And here's the query, and it ran in 40.1 seconds. That's the wall time. These times add up to more. I am still trying to figure out what this is based on. Not very successfully, but like I've timed it before with a clock. The wall time is the accurate time in terms of how long this took. So it's about, you know, not a huge result set. We got about 1 million rows after, you know, processing all these where clauses and ordering and whatnot. But if we look real quick at the logs, and that'll be right here, there's actually a place where we can see, hold on. Actually, this might be the wrong log. There we go, sorry. So we can see here that it's actually, you know, caching a lot of this information into CPU. I'm gonna see if, I don't think it would have had to have hit the disk. Oh, look, it did the disk too. So here it's cached both into disk and CPU. So it's been able to go not only bigger than GPU memory, but system memory as well. So we're gonna take a quick pause on this demo, and I'm gonna kind of show you what this looks like on the Blazing side. So here we have that relational algebra on the left. I'm gonna make that a little bit bigger so that you all can see. And the way that the relational algebra works is it goes from deepest to like you start processing in the deepest node and kind of work your way up. So this Blazing table, this bindable table scan here maps to this one right here, this top yellow circle. And so all of these kind of nodes in the relational algebra get converted into one or possibly multiple nodes over here on the right-hand side. Like you'll see that here we have a logical join that actually gets divided up into a partwise join and followed by a project and a merge sometimes. Here, actually, I think it's missing one of the nodes, but that's just a bug in the visualization. In the actual query, it exists. So what we can see here is that, you know, from 1,000 milliseconds to 2,000 milliseconds of this query execution. So in the first, like in the second of this query, we've got 168 gigabytes of information being read from this customer table, right? At the same time, in this other scan, which corresponds to the line item table, we have 167 megabytes of information coming in there. And it's caching data. Ooh, why can't I scroll down? There we go, with the arrow key I can. And this movement, so the circles are the actual transformations here. They map to these kernels that are actually making transforms. And in between every kernel is this cache, right? And that's that cache that we saw earlier, is this cache which allows us to move information into and out of the GPU as it's being read in. So these arrows represent the speed that it's actually moving through the cache. We need to do a little bit of updating to the thing that generates this graph in order to be able to visualize both the input speed and the output speed, which can be different because one is the speed that it cached and the other one's the decaching speed. This is actually both put together, so it'll be like half as fast as it'll look slower than it's actually operating. But we can actually go and see kind of how information starts flowing, right? So between 2 and 3 seconds, right, it's scanning both the orders and the line item table. There's a lot of filters on the orders table, so it's probably able to get a lot more throughput. That's why you're seeing the higher numbers there in terms of processing. But that kind of explains how, like here we can, when I'm hitting these next and previous buttons, I'm just going through different pictures, which are different slices of the graph at different points in time. So like between seconds 5 and 6, this is everything that's happening in the engine at the same point in time. You'll notice that it starts becoming faster as the query is running. That's because as the query is running, it's gotten estimates from the first couple of chunks, and it's able to make better decisions in terms of scheduling how it moves information through this cache. It'll start being more intelligent with how it divides up partitions, how it can combine partitions when it's doing things like joining or projecting, and whenever it goes into the cache. Some of these caches actually concatenate things together to prevent things from getting too small, or to prevent data frames from getting too small, and we'll split them up when they're starting to get too big. So this is that first query that we ran. Yeah, so that kind of gives you a quick, I hope you guys aren't seeing this, right? Like I'm not covering it up, am I? Hopefully not. Well, not a lot of feedback when you're giving a live session.
Yeah, so, it's good. You're good. You can see it.
Awesome. So going back to the demo, here we have another query. And I'm guessing, as I see this memory utilization go up and down like that, I'm guessing that some of you are running out of memory, and that might be causing some of those dips that I'm seeing. If that's the case, we will definitely work to make sure that this doesn't happen as often in the future. I think we didn't scale up our node rate. Yeah, there it goes. It died. So I'll get back. I think maybe I'm gonna go to, well, no, we should do this again, I guess. So I know what I'm gonna do. I'm gonna open this up in incognito mode and get a new, get put onto a different server, because I might be put onto a server that's particularly slow. And that, let's see. Boom, boom. And yeah, I think this is going to be a better experience. All right. Yeah, we got lucky here. We got put onto a new one. So here we shouldn't see the out of memory issues that we were having before. So I'm basically just going through, running the same cells that we ran before to create the tables. I'm going to skip this query since we already ran it. And I'm going to go down to this cell here where we're running query number 4. It's basically, a nested query where I'm running a very large query on the line item table. So this is actually this is all the data in line item. And then it's going to order and group by whatever comes out of that.
To just clarify, line item is the largest table inside the TPCH dataset and represents about 90% or so of or I think it might be 85% of the total data. So that one's like 85 gigs or so.
Yeah, so we've already created the tables, and now we're running query number 4. And it takes, I can't remember how long this one takes, but it takes like another, I think this one's like 35, 40 seconds. This is actually a lot of data, right? So we're gonna wait for that to finish executing.
While you wait, there's a great question.
Go ahead.
So when I run Blazing TPCH test in my own GPU server with 36 CPU cores, I noticed that a quarter of the CPUs are also busy. Can you explain a bit what is done in the CPU?
Sure. There's a lot of things that have to happen on the CPU, from reading and interacting with metadata to sending messages across TCP, performing optimization calculations, doing things like tracking how many chunks are coming into a kernel. So when you look at like this kind of graph, right? So we have awareness and are polling these different kernels to know how many partitions are they processing, how many bytes on average is each partition. So there's all kinds of calculations that are happening to keep this graph operating as efficiently as it can. And there's also like the network work and things like that. I can say that there's no places where the CPU is being used to look at long buffers, right? So the CPU is not being used on like long buffers or to do big calculations. So here we ran another query that, very similar kind of situation. Here we can see what the relational algebra looks like. And we have our results that are in about 42 seconds. And this is on, a table that I think it's TPCH is 75% of the data. So it'd be 75 gigs. It's a 75 gig table. And we ran that on, a single T4 and caching on both the CPU and disk from GPU. And here we can run our last query. This is one of the more simple queries. It actually has, it's going through line item, making taking a year of information out of it. And then, so it's basically doing a big filter and then just aggregating that, right? So this is kind of a nice query because it kind of gives you an idea of what this plan looks like, right? So this bindable table scan already comes with filters on it. So as it's scanning data from the database, it's running filters on that information. And before that goes to the logical project, a lot of that is going to get cached on CPU until it's needed by this project to actually do the multiplication, right? Between all of these different steps, right, it's able to cache the interim results in any of these different places. Now I want to show you all a demo that, I guess, Rod, are there any questions so far about this that we've run so far that we need to address before I go to kind of showing what this looks like on a bigger instance?
Real fast, just a great follow-up question. So following on that CPU question, what configuration of CPU to GPU should people look for? In other words, number of virtual CPUs versus GPU cores.
That's a very interesting question for someone to ask me right at this moment, because we are refactoring how our communication works a little bit to move it more of it to basically moving it to UCX. And our UCX version of the engine has a lot less thread pressure on the CPU side. It basically needs much fewer threads to accomplish what it was doing before. So that optimal ratio is kind of like difficult to pin down. I would say somewhere between 2 to 4 physical cores per GPU, I think, is often a good trade-off. The more GPUs that you have, the more you can kind of fudge on the number of CPU cores that you have, because they can, share that burden a little bit better. If that makes any sense. There's more overlap.
Felipe, maybe also what we find in practice at Graphistry is the memory also matters. Maybe you can talk about CPU RAM versus GPU RAM and disk, maybe even too.
Sure. So, I mean, the biggest differences are really the throughput that you get between any of these different systems, right? So you're talking wild, like I don't even know what it's at. It's like 800, 740 gigabytes per second, always getting higher is the memory bandwidth that you have on the GPU, right? And on the CPU, you might have anywhere between, you know, an order of magnitude less to maybe 4x less, that kind of bandwidth on the CPU itself, depending on if you're on an Intel 86 or Power 9 system or some other kind of, you know, fancy HPC hardware that I see out there. People get real creative with that stuff. And disk is obviously by far right now the slowest, though we're always, you know, there's always like new technologies and interconnects that are being developed that might be able to increase the throughput between things like, you know, disks and GPUs, specifically high performance disks like NVMe drives. All right, so I'm gonna go over to the last kind of demo here, just to kind of give you guys a little bit of an idea. This is running on 8 GPUs and a DGX2. They're V100s. We're going to be running this on a 1 terabyte data set. The data set that we're using is called TPCX-BB. It is brought to you by the same people that brought you TPCH. And it's exciting because it includes machine learning type stuff and all kinds of fancy algorithms that you have to implement. It's been a wild ride getting all of these queries to work in Blazing with the combination of Blazing and DAS-QDF. But that's what we're going to look at. So here you can't follow along because, like I said, this is running on a much bigger cluster that we've already set up. So I'll just go ahead and kind of like, you know, run these queries. So this is some information.
Felipe, real fast, why don't you explain how BlazingSQL becomes distributed, which you kind of have in that first cell there.
Yeah. All right. So right here, what I'm doing is normally I would use this cluster equals local CUDA cluster, but I think I need to submit a GitHub issue because right now it's scheduling all the DAS workers on the same GPU. So what I did instead was, it's actually pretty simple. Let's see if I have where did I put it? Right here. We had a tiny little script which runs the DAS workers manually and assigns a different CUDA visible device to each one so that I have 8 workers, right? And I attach those workers to a DAS scheduler. This is just a URL for the DAS scheduler, right? Down here somewhere is we're not going to look at the terminal. That's not interesting to anybody. But down there is a DAS scheduler, which has this IP address. It's on the local network interface. We're doing this on 1 node. Could just as well be multiple nodes. It's just for this task, we're doing it on 8 GPUs in a local node. And after I create my client, kind of, you know, the way that you're, you know, however you make a DAS distributed client, right? That's it. I can pass that client to the Blazing context. And now, whenever I run these queries, what we're going to get back here, this result is going to be a DAS data frame. I can show you how that works in a minute. And here I'm initializing a pool, saying what the pool size is going to be. Right here, I'm just, you know, putting in the directory where all this information lies. This is something that's going to be used in the query. And after I create my tables, which are, what is it? Workers? What's wrong with workers? Does not have workers? Give me a second. Hopefully I didn't hose something here, which I might have. It's very easy to do. Just kidding. Oh, I might have timed out from my session on the DGX. Let me
maybe stop sharing your screen for a second.
Yeah.
Depending on whether or not you have passwords or anything.
Nope.
Oh, all right. Never mind. You're good.
Nope. But I do need to restart my DAS scheduler for sure there. So yeah, you'll get to see how it is that we do these exciting things. So I'll go into my Conda environment, and here I'm just going to do DAS scheduler. Interface. Slow. And I'm going to put some port that I think was using 9005. All right. And then over here, just going to connect to the same place, and I'm just going to run them again. All right, so there, I've started up the workers. Great, they're all there. All right, back to the demo. Sorry about that. Now we're reconnecting, and we should be able to see, you know, the client exists. Making sure this is all running. It'll take a few moments to initialize. There we go. All right, now our context is ready. All right, so we're going back in, and now we're creating the tables based on these files. Does it pretty quickly because these are local. It didn't have to go to S3 to find them all. And all right, so here we're running, this first query that we're running is some nested select distincts with some other select distincts around them. That this is basically a join between these two different things, right? And this just ran on a 1 terabyte data set using some of the biggest table in TPC-XBB is this web click streams, if I'm not mistaken. And it was able to run that in 13.2 seconds on that GPU. And if we look at results, it's a DAS data frame, right? Wow, look, just a normal DAS data frame with 8 partitions. How exciting. And, you know, if we do dot head, well, I guess that's what the command below is, you know, we can actually see the information that lies therein, right? So, I mean, it's pretty easy, you know, to just point yourself at these tables and, you know, run these very large out of core capable queries on, you know, a 1 terabyte data set on, in this case, 8 GPUs. Here, we have another query that's a little bit more complicated. There's, you know, some nested selects, a little bit of aggregationing happening up here, and some joins, and there's a bit more happening, right? But you can see, we'll look here at, it can still run this query very quickly. And, you know, just to have a little bit of fun, why don't we, in 7 seconds, why don't we explain that query so we kind of see what, oh, I need to print it if I want it to have the slash ends. There we go. So it's actually a pretty complicated plan that it's able to execute here. A lot of joins going on, right? As you can see, and it's able to, you know, process that actually quite quickly. And be able to leverage, you know, other, you know, not just GPU memory for both for the interim processing and for the inputs and the outputs, which is to us very, very, very exciting. That I think is it for that demo. I kind of want to mention a few things real quick that, you know, this is all these efforts are community efforts. Like we've built this together, we've done this together with a lot of different people, people like Leo, who's here, you know, the DAS project, all the people at NVIDIA that work on RAPIDS. You know, we've all been working on this stuff together, and it's been a very exciting ride, and we're always looking for more people to go file issues on GitHub, right? Please file issues. It's very useful to us. Contribute when you can, you know, You want to throw in a new file format, have at it. Like, we'll help you, we'll teach you, we'll tell you what needs to be done. So we're definitely looking for always to get more help in building this project. That's a great way that you can support our efforts. And yeah, and I kind of wanted to mention, as Rodrigo usually does, you can see us on Anaconda. If you want to, on the BlazingSQL or the BlazingSQL nightly channel. You can look at us on BlazingSQL notebooks by going to app.blazingsql.com. And you can launch your own GPU data science workstation on the AWS Marketplace. Just look for BlazingSQL on the Marketplace. Any questions?